Good morning, dear students. Welcome to Deeksha Online. Today we'll discuss some of the problems in hydrocarbons. This unit includes alkane, alkene, alkyne, and aromatic hydrocarbons. Let us take the first example. The combination of diene and dienophile which can give the following product. So we need to find out which diene, which dienophile can give the following product. So the structure is given. So options are given as this. So before we go to the option, let us solve the problem, then uh, map for the given options. So if I take the reaction, this is based on Diels-Alder reaction. Diels-Alder reaction. So first I'll just go through the reaction. So it is a combination of diene and dienophile. So conjugated diene, that is buta 1 comma 3 diene I have taken, and dienophile as ethene. So there are 6 atoms, 1, 2, 3, 4, 5 and 6. These 6 atoms are involved in the reaction. It's a cyclic cyclization reaction. So this pair of electron will move to here to form a bond. The pair of pi electron will move to 1 to form a bond, and the pair of pi electron from 2 comes to bond between 2 and 3. So I'll get a cyclic product, that is cyclohexane, with one double bond between 2 and 3. So 1, 2, 3, 4, 5, 6. Rest all other groups attached to either diene or dienophile will remain same. Now, as per the given question, we require the product as this. So this is the product what is desired. So the double bond is very clearly between 2 and 3. So if I take this double bond, so I can number this as 1, 2, 3, 4. This can be 5 and 6. So if I want to write the diene now, diene is this. So this is 1, 2, 3, 4 and 5 and 6. 5 and 6. Now attach the remaining attachments. So 1 and 4 have no other groups. 2 and 3 has 2 methyl groups. So this is the diene what I have to take. And 5 and 6. 5 will have pH and 6 will have carboxylic acid. So this is the diene and dienophile combination which can give this product. So 2 comma 3 dimethyl but 1 comma 3 diene and 1, 2, 3, 3 phenyl propanoic acid, propanoic acid. Okay, so we'll go to the options now. So if you carefully look at this, so option B will match. So but 1 comma 3 diene with 2 methyl groups and 1 pH and 1 COH in the double bond. Answer is B. Let us go to the next question. What is the correct order of reactivity of the following compounds towards electrophilic addition? It is electrophilic addition, not substitution in the benzene ring. So there is a double bond in the side chain. So we need to find out the reactivity of that alkene towards electrophilic addition. These are the 4 options given. So the main concept of this reaction, if I take electrophilic addition of alkene, the intermediate is carbocation. So in this particular example, if I go to the solution, see in most of the all the compounds you have a benzene ring, and this is the common group present in all the compounds. So when I react this with H plus, So it is going to form a benzylic carbocation. Benzylic carbocation. So COH is there in all the compounds. So the carbocation stability depends on the groups present in the benzene ring at ortho or para position. So any electron releasing group at ortho and para increases stability, and electron withdrawing group at ortho and para decreases stability. So the stability is decreased, means rate of reaction decreases. As a result, the groups which are destabilizing will have less reactivity. The groups which are stabilizing will be having high reactivity. Since it is a carbocation, plus I and plus R will stabilize, and minus I and minus R will destabilize. Okay, so this is the concept what we have to apply. So let us go to the options now. So in the first compound, there is no other group present in it. In the first compound, there is no group present in. In the second compound, we have a nitro group at para position. In the third one, I have OCH3 group at para position. In the fourth one, I have CH3 group at para position. Nitro group is minus I and minus R. CH3 is plus I and plus R through hyperconjugation, and OCH3 is very strong plus R. So plus R means this will be highly stable. So this is 1, highest reactivity. Then comes methyl, which is 2, which is going to be more reactive. Then without any group, this becomes third, and the fourth one, least one, is with a nitro group. So answer should be 3, 4, 1, 2. So answer should be 3, 4, 1, 2. We'll go to the next question. Example 3. We have to identify the end product in the following reaction sequence. So we have given 3-step reaction: hydroboration, oxidation, then reaction with concentrated sulfuric acid, and then reaction with dilute sulfuric acid. So we'll go to the solution. So the compound given is a cyclopentane ring. Sorry, cyclopentane ring I should write. Okay. Cyclopentane ring. Attached to it one ethyl and then one ethyl with a double bond. So first step is hydroboration oxidation. So B2H6 THF, then H2O2 OH minus. All of us know hydroboration oxidation is anti-Markovnikov addition of water molecule, which follows syn addition reaction. So if I go with that logic, I have to add water according to anti-Markovnikov rule. That means OH will come to the carbon with a more number of hydrogen. This is the first product. Then the second step is concentrated H2SO4. So for an alcohol, when I react with concentrated sulfuric acid, it is acid catalyzed dehydration, which follows carbocation mechanism. Now if I take the same step, so first carbocation is formed here, which can rearrange to form secondary, and then finally can form alkene like this. So this is the alkene which can be formed. Now the alkene is reacted with dilute sulfuric acid. So I'll take the next slide for that. So this was the compound we had. This is the Now when I add dilute sulfuric acid, again the carbocation formation takes place. So this time carbocation will be tertiary and it is attached to cyclopentane ring. There is a possibility of ring expansion. So when the ring expansion takes place, it becomes 6-membered ring. The 6-membered ring, so the ring is going here, one carbon will have both methyl and ethyl and the other carbon will have the positive charge. Again there is one more shift possible, methyl or ethyl shift. So if you remember the carbocation rearrangement, the order of migratory aptitude would be 3 degree, 2 degree, 1 degree and last is methyl. So methyl and ethyl are available. Ethyl shift is more preferable. So ethyl shift takes place forming the carbocation like this. This becomes methyl, this becomes ethyl. Now the water should attack because it is dilute sulfuric acid. You are adding water. So this will become, this will be ethyl and this is going to be OH group. So this is the final product. So cyclohexane with one methyl and OH on the same carbon and the next carbon will have ethyl group. So we'll go to the options now. If I look at the options, I can see here methyl and OH. In the first option, I have the same requirement. The answer is A. The next question, example 4. Two compounds are given, reacted with one equivalent of hydrogen. In platinum catalyst, you have to select the correct statements. So both A and B gives 1,4 addition product and both A and B give 1,2 addition product. A gives 1,4, B gives 1,2 or A gives 1,2 and B gives 1,4 addition product as major products. So to verify which one can undergo 1,4, which one can undergo 1,2. Okay. So we'll go to the solution. So if I take the first one, there are two cyclohexane rings and there is one double bond here, CH2, and there is one more double bond here. Now this appear like a cis-diene. Okay, so I'll write it once again. It's not very clear. So this is like a cis form. So hydrogen comes to attack. Okay, so it can form an intermediate like this. So this can partially bond to this can partially bond to this double bond can go here. So as a result, this pair of electron will come here. So I can write a transient state. So this can be moved here, this can go here and this can come here. So a 6-membered cyclic transition state is possible. So this will give 1,4 product as a major product. So double bond will come here, this becomes CH3, this double bond will here and this will get 1 H. In the case of second molecule, the second molecule is this. So it is actually S-trans. So S-trans cannot form such type of cyclic intermediate. The double bond outside the ring is generally relatively more reactive towards hydrogenation. So the hydrogenation takes place for the double bond in the outside the ring. So it becomes H2 equivalent. So this will be forming this product. It's going to form 1,2 product. No question of 6-membered, it is only 4-membered cyclic intermediate. So HH will come here, this is going to be the cyclic intermediate. or transient state, right? So 1 comma 2 product for the second one, 1 comma 4 product for the first one. So answer would be compound A gives 1 comma 4 addition and compound B gives 1 comma 2 addition. Answer C is the right answer. Example 5. A hydrocarbon with a molecular formula C6H10 forms an insoluble salt with silver nitrate in alcoholic ammonia. Acid catalyzed hydration of the compound gives only one ketone with formula C6H12O. The oxidation with KMnO4 in acid medium gives a carboxylic acid with C5H10O2. The organic compound is. So here we have reaction, that is forming an insoluble salt with silver nitrate in alcoholic ammonia, which is nothing but Tollens reagent. And a hydrocarbon is giving precipitate with Tollens reagent means it has to be a terminal alkyne. So if I take the option here, there are 3-methyl, 2-pentyne, methylene, cyclopentene, 3-hexane and 1-hexane. So I have 1-hexane as the terminal alkyne which is present over there. So we'll verify that reaction for all the three situations. So we'll go to solution. So if I take 1-hexane, 1, 2, 3, 4, 5, 6, 1-hexane. So with AgNO3 in ammonia, Tollens reagent, terminal alkyne, it can form C minus Ag plus. This is first point. The second one. So acid hydration means it is HgSO4, H2SO4. So it will form always terminal alkyne, always form ketone, only one ketone. If it is a non-terminal alkyne, it can give isomeric ketones. It's a Markovnikov of addition of water. So you get an enol, convert into keto. So you get only one ketone. And same way, if you take KMnO4 oxidation, H plus. So the triple bond completely breaks, the terminal alkyne becomes CO2 and the next 5 carbon atom become carboxylic acid. So 1, 2, 3, 4, 5. So this is going to be carboxylic acid, C5H10O2. So all the three conditions satisfying for 1-hexane. So answer should be 1-hexane, that is C. Example 6. Which of the following is the best method for the following conversion? So what is given here, you have an alkene, finally it is becoming an aldehyde. Two steps are given, we have to identify the reagents. So the options given, so we have to see the options. These are the options available. So I have to verify the question for each and every sequence what is given. So let us go to the solution. The first one is hydroboration followed by PCC. So we'll see what is the exact thing happens. So the reactant is this. So hydroboration oxidation, B2H6, THF, H2O2, OH minus. So this will become alcohol. So I have to add OH here. Okay. Then you are reacting with PCC. So PCC will oxidize the primary alcohol to corresponding aldehyde. So I am getting directly the expected product. So B2H6THF then followed by PCC is able to convert the given conversion, but still we verify for other three also which is the best they are asking. We can go for the other options also. So the first one is working. So I'll go for the second one. I'll go back to the options. So again hydroboration oxidation, HiO4. HiO4 means you have to require diol. So in hydroboration oxidation you are getting only one alcohol. So B option is not at all possible. The third one, H2O, H2SO4 and PCC. We'll see what exactly that will give. So the reactant is this. We have H2O and H2SO4. So it is basically dilute sulfuric acid hydration. So it is a hydrolysis through acid catalyzed hydration. So it is going to form first carbocation. So carbocation is secondary. Rearrangement also will give secondary. So once you add water, so you're going to get OH here, secondary alcohol. This when you react with PCC, I'm going to get a ketone, not aldehyde. So this option is also not giving the product what is desired. So this third one is also ruled out. The fourth one, osmium tetroxide and dichromate. Osmium tetroxide will give diol to alkene, and potassium dichromate is going to be very strong oxidizing agent. It can convert the terminal alcohol to even acid. So this also is ruled out. So option A is going to be A. Example 7. An alkene on ozonolysis forms the following products. What is the structure of the alkene? So alkene is giving one butane dioic acid and one molecule of acetone and one molecule of formic acid. Okay, so this is oxidative ozonolysis because H2O2 is present. It is oxidative ozonolysis. So these are the options given. So we have to verify each one for oxidative ozonolysis reaction. So we'll take one by one. So the first one, I have a cyclobutane ring, you have one double bond, one methyl and one isopropyl group. So if I break this ozone and H2O2, so double bond breaks completely. So it is both are going to be forming a ketone. So it's going to be this one ketone and this will be another ketone. So I'm not getting any acid, so it is not the solution. So it's going diketone, only one product is formed, it is not going to work. So we'll take the second one. Before that I'll just check the structure of second one. Okay, the second product reactant is you have an isopropyl group kind of a structure, then continuous chain like this, one double bond here, one double bond here. If I break this through ozonolysis in H2O2, so double bond completely breaks here. Here also double bond completely breaks here. So there's a terminal carbon that converts into formic acid. Now this part, what I can see here, is becoming acetone. Then this is becoming carboxylic acid. Even this carbon also become carboxylic acid. So this will be COOH, then two CH2 groups, and then COOH again. So all the three products what is given in the question is obtained. So answer should be 2. So answer should be B. So if you verify for the other two also, if I take here only, so double bond can be broken here. Here also it can be broken. So it forms acetic acid, CH3COOH from here. So it is not one of the product. And here what happens, this central carbon becomes carbon dioxide. So both C and D are not giving the expected product. We'll go to example 8. Which of the following product is formed when 1,2,4-trimethyl cyclopentene is catalytically hydrogenated? So 1,2,4-trimethyl cyclopentene is hydrogenated. Okay, so we'll go to the solution first, then come back to the options. So 1,2,4 trimethyl cyclopentene. So cyclopentene is this. So this is 1, 2 methyl groups. 1, 2, 3, 4. I have methyl group here. This is H is also present. There is a double bond here. So cyclopentene. So this is hydrogenated. So H2 nickel. All of us know hydrogenation, that catalytic hydrogenation is a syn addition. That means the hydrogen can come from one side of the double bond. So in the product, both methyl can be in wedge or can be in dotted line. But the above carbon, what CS3 and H, whatever is there here, that is going to be fixed. So I can get, let us say this is CH3 and this is H. So I can get all CH3 like this and H will be on the other side. This is one. Or CH3 can be in dotted line, H can be in wedge. And here the same thing will remain. So since this is also not given, I can take the other option also. So both are going to be the same. So CS3, all three can be either in dotted line or in the wedge, but these two at 1, 2 position, these two cannot be one in wedge, one in dotted line, because it is syn addition, both methyl group, either they should be in wedge or they should be in dotted line. So we'll see the options what is given. So in the first example, you can see both methyl groups are in the wedge. Third one can be in wedge, can be in dotted line. So this is definitely a possible product. So in the second example, second option, I have one methyl in dotted line, one methyl in wedge. So this is not possible. Third one again, both are in dotted line. Again CS3 is in wedge. This is possible. And fourth one, again one is in wedge, one is in dotted line. It is not possible. So 1 and 3 is possible. So option C is the answer. Example 9. Consider the following reaction sequence and choose the correct statements. So reaction sequence is, I have 2-methyl butane, NBS, then sodium ethoxide and ethanol, major, and hydroboration oxidation. So clearly indicates NBS means it's bromination through free radical mechanism. Then second step is dehydrohalogenation, and third step is hydroboration oxidation. So let us see the solution first and then we will come back to options. I have 2-methyl butane. So NBS. So most preferable position is tertiary. So bromination, free radical selectivity is more for bromination. So I'll get this as the major product. Now second step is dehydrohalogenation, that is C2H5ONA and C2H5OH. So this is dehydrohalogenation, E2 elimination and following Saitzef rule. So the double bond should be towards right in the major product. This is the major. The third step is hydroboration oxidation. B2H6, THF, H2O2 and OH minus. So anti-Markovnikov addition of water. This will be the product. So it's going to be 1, 2, 3, 4. So it is 3-methyl 2-butanol. That is the end product in the sequence. So we'll go back to option to see what and all is given. The first step is ionic bromination at tertiary carbon. So first step is ionic bromination at the tertiary carbon. It is free radical mechanism, so it is wrong. Q is a mixture of stereoisomeric alkenes. So alkene is not having geometric isomers because two methyl groups are present. So it is not showing any geometrical isomerism. The compound R is 3-methyl 2-butanol, which is correct. And R is a racemic mixture. It is not having chiral center. So R is a racemic mixture, correct? Because what happens is we get 2-butanol. So it's going to be chiral center. So the compound is this. So this is a chiral center. I get racemic mixture. So answer should be C and D. We'll go to the next question. Which of the following is correctly matched for products? So 4 options given. We'll check for one by one. So we'll go to solution. So the first one, two double bonds plus CHCl3 KOH. So CHCl3 KOH will give CCl2 as carbene. So this will form two chlorine atoms like this, cyclopropane ring, and the hydrogen which is present here is acidic. Because of OH minus present in the same medium, it will take this proton. So this comes to form a double bond here. The ring expansion takes place and one of the chlorine leaves. So this will form directly chlorobenzene. Okay, the first conversion is correct. We'll go to the next second one. Actually, double bond should be present here. It is missing. And option B, you have a alkene and same reagent. So this will also produce carbene. We'll see what happens. It is cis-2-butene is the reactant. So cis-2-butene HHCH3 CH3 and same CCl2 carbene. Carbene to alkene is always forming cyclopropane derivative. So the stereochemistry will be maintained. So CH3 will be in wedge or dotted line. So if I put dotted line, this will be wedge, this will be wedge, and this will be dotted line. And 2Cl will also be here like this. So either both methyl can be in wedge, both methyl can be in dotted line. So it cannot be opposite because cis alkene will give cis cyclopropane derivative. So the second option is also correct. So first one is correct, second one is also correct. The third one, I have taken trans 2-butene CH2N2, same thing. So CH2 is the carbene. So again cyclization, and here you can see CH3 are trans to each other also. So this is also correct. And fourth one, you are using MCPBA followed by hydrolysis. So it's going to be trans 2-butene again. So we'll go to the solution for that. Trans 2-butene MCPBA will form epoxide followed by hydrolysis is anti-hydroxylation. So we know that car and time. So transalkene anti-addition meso compound. So I should get meso compound as the product. So 2 CH3 group in the vertical line, 2H will be here, both OH on same side. It is meso compound I should get. So according to the given option, what is there we will see. So in the fourth one I have OH opposite. So it is a racemic mixture given, which is not correct. So answer should be A, B and C. Example 11. Which of the following decarboxylation products are correctly matched? So decarboxylation reaction can be done in two ways. One, RCOOH with NaOH and CaO gives RH. This will go through carbanion R minus, whichever forms most stable carbanion can be easily undergoing decarboxylation. The other one is just by heating. So here we have dicarboxylic acid like malic acid. When you heat, it loses CO2, become CH3COOH. So if two carboxylic acid groups on the same carbon, that can be heated and decarboxylated to form monocarboxylic acid. And most importantly, if I have beta keto acid on heating loses CO2, forming the corresponding ketone. So it need not be beta keto always. It can be beta unsaturation. A double bond or triple bond should be present at the beta carbon, beta gamma atoms. So we'll see the options what is there. This is about decarboxylation. So we'll see the options. The first one, this is going to be normal carboxylic acid. So in normal carboxylic acid, NaOH and CaO, it is going to eliminate CO2. It's going to be forming, should form propane, which is not the correct answer. Okay. In second one, this is carboxylic acid, this is alpha, and Cn is beta. C triple bond N is beta. The C triple bond N is present. So at beta carbon there is unsaturation. So carboxylic acid can be knocked out to form respective compound. Cyanide here. C and D. If I go for A and B, so this one is 2 carboxylic acid group decarboxylated, forming cyclobutane with a single bond. But in NaOH decarboxylation will give corresponding cyclobutane. And this again has beta keto alpha beta. So beta keto acid forming ketone. So here it's going to be wrong, not exactly. So it's going to be B and C should be the right answer. B and D should be the right answer. So answer is given as A, B, C, D because this is first considered as decarboxylation followed by electrolysis forming the free radical and joining. So the question was intended to cold electrolytic method, but the first and third one are based on that concept. So I would say answer only for decarboxylation answer should be B and D, not A, B, C, D. Identify the relation between the products. So there is sequence given. So alkyne NaNH2, CH3I, liquid ammonia and bromine and CCl4. So we'll see what are the possible products. So we'll go to the solution part. So I have cyclohexane and then one triple bond like this. So terminal alkyne, first step is NaNH2. So forming sodium salt minus Na plus. Then you react this with CH3I minus sodium iodide. I'll get triple bond with CH3. Now sodium or lithium in liquid ammonia, Birch reduction. Birch reduction will give me transalkene. So cyclohexene, H double bond H and CH3. It is trans. Then you are reacting this with bromine in CCl4. So bromine in CCl4 is anti-addition. So trans and anti-addition give meso kind of compound because both are not same. So I'll be getting the meso compound in this format. I'll write here. So top group and bottom groups are different. So it is going to be cyclohexane ring and here it is CH3. So this is Br, this is Br, this is H and this is H. So since it is not symmetrical, it is going to be always racemic mixture. So the product is a racemic mixture or an enantiomeric pair. So we'll go to the options now. So identical molecule wrong, enantiomeric pair is right. So it's a racemic mixture. Example 13. Which of the following statement is or correct? Okay. So iodine does not react with ethane at room temperature even though I bond energy is minimum. So in free radical halogenation, we know that the order of reactivity is chlorine, bromine, fluorine, chlorine, bromine and iodine. So uh, the bond energy of iodine is going to be much lesser, but in propagation step, the iodination step will be highly endothermic. So reaction almost becomes very less in rate. So though iodine is going to be easily broken down to form iodine radicals, at room temperature, the reaction is not feasible in the subsequent steps. So the first statement is correct. Iodine does not react with ethane at room temperature, but chlorine, bromine react very rapidly. So this is the correct statement. The free radical addition of HBr and electrophilic addition of HBr to propene give the same product. Propene is an unsymmetrical alkene. Free radical mechanism will be anti-Markovnikov rule. Electrophilic addition will be a following Markovnikov rule. So they cannot be same products. So it is going to be wrong statement. The rate of bromination of methane. The rate of bromination of methane decreases if HBr is added to the reaction mixture. So the bromination rate decreases because HBr is one of the product. So you're adding another product, the equilibrium is driven in the backward direction because bromination is already a relatively slow process. It is almost in a reversible condition. So the moment you add HBr, HBr is a byproduct. So when you're adding a product, reaction goes in the backward direction. So the rate of bromination decreases. The fourth one, this is a correct statement. And fourth one, allyl chloride adds halogen faster at corresponding to vinylic chlorides. So we'll just see what exactly is that mean. So if I take allyl chloride means CH2 double bond CH single bond CH2 Cl. If I add say chlorine here, so it will form cyclic chloronium ion. And I have CH2Cl. If the bond is broken here, this is not forming carbocations. If the bond breaks here, the positive charge on this carbon is stabilized by hyperconjugation and plus psi effect, mainly hyperconjugation of two hydrogen atoms. But in case of vinyl chloride, what will happen? So vinyl chloride is CH2 double bond CH single bond Cl directly attached to it. So if you add chlorine to this, I'll get again cyclic chloronium ion. So this momentary it breaks, it is going to have minus I effect. As a result, the stability of the cyclic halonium ion, it is not forming carbocation. If it is complete carbocation, then chlorine can donate its lone pair to form the octet stabilized resonance. But here not a carbocation, as a cyclic chloronium ion, the chlorine atom is acting as a minus I group, CH2Cl is acting as relatively stabilizing hyperconjugating group. That's why the rate of reaction is more for allyl chloride. So if I see the options now, except the B, all three are right. A, C, D is the answer. Example 14. Which of the following compounds undergo bromination at a faster rate? This is aromatic nuclear electrophilic substitution reaction. So ES reaction, we need to take everything into account. So the sigma complex stability will matter. So we know that uh, electrophilic aromatic substitution reactions, in that you have benzene ring. If I have one more group, say group G, if G is electron releasing, then activating group, ortho and para directors. If G is electron withdrawing, it is deactivating and meta directors. Okay. Now, if you carefully look at the given molecule, so let us go back to the slide. So in the first one, I have benzene with a cyclohexane ring attached to it. So this will be like alkyl group. So it is a plus I group or hyperconjugation. So it is an activating group. And here nitrogen is attached directly to the benzene ring. Nitrogen lone pair can come into benzene ring. So it is more activated. And in this there is nitrogen but not directly attached to benzene rings. It acts as a minus I group. So less than even 1. And the D option, you have a carpooling group attached to benzene ring. So it is minus R effect. So the most reactive is B, then A, then C, then D. So they are not asking for the order, I think. Answer is B. So because of the nitrogen directly bonded to benzene ring, it is like aniline. Aniline and phenol, they are all very highly reactive towards electrophilic aromatic substitution. So aniline will undergo tribromination in presence of bromine water. So answer should be B. Example 15. What is the end product of the following reaction? So this is going to be again electrophilic aromatic substitution, that to acylation reaction, followed by zinc amalgam and HCl and HF. Okay, so we'll take the solution. So we have ethoxy benzene, OC2H5. OC2H5, all of you know it is an ortho and para director. So para is predominantly product formed because OC2H5 is bulky. Para is major. This is reacted with cyclic anhydride. So acylation in presence of AlCl3. So this bond breaks. So it goes here, goes here. This will join the para carbon. So what I get is OC2H5 will be here. This becomes ketone and 2 carbon atom, then it become acid. This is the first product. Then you are reacting this with the zinc amalgam and HCl. Clemenson's reduction. Ketone become CH2 group. So what I get is benzene ring with OC2H5. Now this will be like 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, and this will be COOH. Now you are reacting this with HF. So this will be cyclization. There is a hydrogen at the next position. This H and this OH will be going out, forming a 6-membered ring. So it is OC2H5. So this will get cyclized. Ketone is coming over here. This is cyclization product. This is the end product in the sequence. Okay, so we'll go back to the option, find out what exactly is given. So if you carefully look at that, there are two para position product. C is the major. You can see very clearly ketone is in the right position. So C is the answer what we got. Example 16, products of A and B respectively are. So here it is given, one is pyridine and other one is pyrrole. So it is electrophilic aromatic substitution, nitration. So we need to know one thing here. In EAS reaction of pyridine and pyrrole, this concept is by knowing the stability of the sigma complex formed. By resonance, we can make out that, you should remember this, in pyridine, the substitution is always happening at position 3 from nitrogen. So any electrophile in pyridine is always taking into position 3. This is always major, because at 1 and 4 the nitrogen will get electron deficient structure in the resonating forms. In case of pyrrole, the electrophile always prefers to attack at the second position next to nitrogen. So that is the major product in both the cases. So pyrrole and pyridine have specific reaction in case of electrophilic aromatic substitution. So if you carefully look at the options given, so pyridine should be 3 and pyrrole should be 2. So option B. Okay, remember this concept. In pyridine, the substitution is more preferred at position 3, and in pyrrole it is next to the nitrogen atom. Example 17. Which of the following reactions are wrongly matched for the products? Okay. So first one, it's based on again electrophilic aromatic substitution. So if I take the first one, it is going to be acylation. CH3CO twice O is acetic anhydride. So acylation. So bromine is an ortho para director, though it is deactivating, but ortho and para director. Halogens are the exceptions, where ortho para directors but deactivators. So this will give para as a major product. So this is a correct reaction. Now here in the second example, same acylation, but I have one CH3 group here, one isopropyl group here. So among CH3 and isopropyl, if inductive effect is taken for stabilization of sigma complex, isopropyl is a stronger inductive effect. But hyperconjugation is always stronger compared to inductive. So methyl is stabilizing to a larger extent compared to isopropyl. So it will preferably go to ortho or para to methyl, not to isopropyl. So this is also correct. In third one, this is specific reaction we should know. Same reactant, but I am taking a different acid chloride. So I'll go to the solution box for this. See, if I take CH3, C, CH3, CH3, C double bond O, Cl. So with AlCl3, it's going to form first AlCl4 minus, forms a carbocation, that is CH3, C, CH3, CH3, C double bond O plus. Now, this particular compound, because of the tertiary butyl group is present and tertiary butyl carbocation is exceptionally stable, so what happens? This electron pair will be lost like this. So it's going to be going out as carbon monoxide and forms the tertiary butyl carbocation. We don't get acid chloride, we don't get ketone, we get tertiary butyl benzene. So you get tertiary butyl carbocation attacking the benzene ring. This is a specific case. Whenever we have tertiary butyl with COCl, the carbon monoxide is eliminated, forming tertiary butyl carbocation. So if I see the options now, tertiary butyl carbocation. So here I have written ketone only here, which is wrong. And NO2 nitrobenzene Friedel-Crafts acylation. So it should have been the AlCl3 is missing here. So if I write AlCl3, nitrobenzene, all of you know it's very highly deactivated, and highly deactivated ring will not answer Friedel-Crafts reaction. So no reaction is correct. So answer which is incorrect is C. Question number 18, a sequence of reaction. You have to identify the last product, that is P. Okay, so we'll go through the sequence. So we'll go to solution. So it is toluene. Okay, first excess nitrating mixture. So HNO3, H2SO4. So toluene is an activated molecule. I can get trinitrotoluene with little difficulty, but you can get trinitrotoluene. Then next step is excess of tin and HCl. This also excess. So all three nitro group convert into amine group. NH2, sorry, NH2, NH2. Then excess of NaNO2 HCl. Diazotization, all three will become diazonium salts. So N2 plus, N2 plus, N2 plus. Now when you add water, nitrogen goes. This will be replaced by OH group. OH, OH, OH with CH3. Then finally you are oxidizing with KMnO4. This CH3 is becoming carboxylic acid. So that's the product, carboxylic acid with 3 OH groups. So I'll go to the options. So if I see the first one, 3 NH2 group, in B option I have COOH and 3 OH groups. Answer is B. Example 19. Which of the following molecules can form tribromo derivative when reacted with bromine water? So all of us know phenol and aniline can form tribromo derivative with bromine water. So, but if I have groups like sulfonic acid and carboxylic acid group with bromine water reaction, these two groups will be generally knocked out and forms tribromo derivative. So first one definitely yes, it will form tribromo derivative. Second one, SO3H group is knocked out. This will also form tribromo derivative. And phenol is here, SO3H and COH both will be knocked out to form tribromo derivative. Now I have OH and NH2. NH2 will not be knocked out. It can form 2 here and tetrabromo derivative can be formed here. So OH orthopara and nitrogen also orthopara. So all 4 positions can be substituted by bromine. So this will be forming tetrabromo derivative, not tribromo derivative. So answer should be A, B and C.